just kind of doing an overview of what to expect during this semester. Today we'll kind of dive right in, but we're actually going to start a little bit even further back than what we had talked about last time, and we'll spend here the majority of chapter 1. We're going to review some some general concepts from Algebra 2. So these are some ideas that you guys would have seen last year in your classes. So we'll start with the most fundamental definition from that algebra class. So we'll define what a function is. Uh-oh. Okay. So we say that a function is a set of ordered pairs with inputs from a set D and outputs from a set R, such that every member of D is paired with exactly one member from R. These sets D and R we refer to as the domain and the range. And if you remember back from your Algebra 2 class, there's a couple of different ways that we had to represent functions. And we'll talk about some of those different representations here for a bit and how we can identify whether something is a function or not in each of those representations. So the first representation we'll talk about are mapping diagrams. So in the mapping diagram, we draw like two circles, one to represent the set D and one to represent the set R. And then we'll put like points inside of each of the circles to represent the members of those sets. I'm just going to label them arbitrarily as like x1, x2, x3, and y1, y2, y3. But they could be numbers or whatever. And then what we do is we draw arrows from each arrows between the members of these two sets to represent how they're paired together. So if we look at this mapping diagram, does this mapping diagram represent a function? Yes, right? If we go through our definition, we need that each member of the domain is paired with something. Okay, they each have an arrow going somewhere, and they can be paired with only exactly one thing. So each of them, come on. There we go. Has just one arrow coming from them. Everybody good with that? Let's look at a couple more examples. Hi, Michelle. Did you check in?
Yeah.
Okay. How about this one? Is this a function? Paul?
No.
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 Great. That's perfect. Yeah. So the issue here is that we have one member of the domain that doesn't have an output paired to it, or paired with it, so that would not represent a function. How about this one? Paul?
Still no, because the domain has to have exactly one output.
Okay, which one in particular is the problem?
X3.
Yeah, X3. Did it matter that Y3 doesn't have anything going to it?
Only the domain, because it's an output. There could be many different types of outputs.
Perfect, good. Yeah, so the all that we care about when determining a function is the domains. So whether all the ranges are used or not, doesn't matter. If only one range is used, like if everything is going to one range, that's fine, not a big deal. All we really care about is what's happening with the domains. Everybody feel okay about this? Again, this should be things that you at least recognize that we did in Algebra 2 last year, probably at the beginning of the year was when you did this. So if it was like a little bit of refreshing here, that's good. But it should at least be like, oh yeah, okay. Kind of remember that. Another way we can represent a function is with a formula or an equation. So let's say we have the formula y equals x squared plus 2. And we're asked, does this define y as a function of x? So this phrase here at the end is really important because it's indicating which one of the variables is the independent and dependent variable. So it says defining y as a function of x tells us that y is the dependent variable and x is the independent variable in this case, which is kind of the way we'd assume from looking at the way this is written, right? In our Algebra 2 class, we always wrote y equals, and we assumed the y was the dependent and the x was the independent variable, right? But we probably on sight can't recognize whether that would represent a function or not because there's not a lot of information in just the equation. What might we want to do, Paul?
You could graph it.
Good.
I believe it's points overlap.
Okay, so we could look at the graph, right? X squared plus 2 is what kind of function, Mackenzie? It's what? It's not linear because it has x squared in it. Right, and that's what we'll do once we have the graph for sure, yes. Does anybody recognize x squared plus 2? What kind of function is that, or type of thing is that? Yeah, go ahead. Okay, so it's quadratic, and the shape of quadratics are all parabolas. That's correct. Very good. You're just one step ahead, but that's fine. Did you guys remember how to tell if the parabola is going to open up or open down? Not really. I'm just reviewing. Yes, Mia? Yeah, so if you look at the leading coefficient, if the leading coefficient is positive, the parabola will open up. If it's negative, it would open down. Here the leading coefficient is 1, so we'd have a parabola that opens up. And what does the plus 2 at the end of this do?
It raises the graph.
Yeah, very good. So it's just going to affect like the y-intercept, right? So my parabola is going to look something like this. Again, I don't really care the specific points are on this. I just need a shape so I can attempt to do a vertical line test, as Mackenzie suggested a moment ago. So when we draw our vertical line test, what we're looking for is any place where the graph might intersect a vertical line more than once. And no matter what vertical line I draw, it's only intersecting the graph one time. So this would be a function. Everybody agree with that? Paul?
So what if it was, it says find y as a function of x. What if it was find x as a function of y? Like, how does that statement change?
So if that were the case, what we'd probably want to do is isolate the x as the independent variable. And then square root both sides. And if you were to attempt to graph this then, what you'd end up with like, is something that looks like this.
Okay. So
and that would not be a function. Yeah,
so
very
it's just
good.
telling you what variable it wants you to kind of like look at.
Yes, yeah. So depending on which variable is the independent or dependent variable, makes a big difference in determining whether something's a function or not, right? Now, in our Algebra 2 class, we always assumed that the x was the independent variable and the y was the dependent variable. And that's kind of the general convention. But there's no reason it needs to be that way. That's what the phrase at the end was doing, was just being expressly clear about which one is the independent or dependent variable. Okay? Cool. Everybody's good about with the vertical line test and all that jazz? That tends to be one of the things that students remember the most. That one tends to stick pretty good. Another representation similar to an equation is function notation. So by function notation, I mean like y equals f of x. And really what this is saying is just y is the value of f at x. So if I was thinking about it as like a mapping diagram. Yoo-hoo, stylus, where did you go? So my x turns into a y when I apply the function or the set of instructions that are called f to it. So this y is really the same thing as like the transformation of x using the function f is kind of what we're saying there. In general, does this make, whether I say something as y equals yada 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 or f of x equals yada yada yada, is there really any difference there? Not really. The only advantage of the f of x is that you're clearly stating which variable is the independent variable. That in that case, the x is clearly the independent variable and the f of x is the dependent variable. And then there's some like notational advantages to this. For example, if you have something like f of x equals 3x minus 4, If we ask you what is f of 2, well, that's just an instruction that tells you to plug 2 in for x, right? That result would imply then that the point 2 comma 2 is on the graph of f of x, or that 2 comma 2 is a solution to the two-variable equation y equals 3x minus 4, right? So it just provides a convenient notational way to talk about plugging values into a function, right? Yeah, Paul?
So it just basically means you're just trying to solve for something more convenient than trying to solve.
It has some like notational conveniences,
Okay.
yeah. So like instead of saying, okay, I'm going to plug x equals 5 into y equals yada yada yada, you can just write f of 5.
Okay.
You know, like,
Is that why it's the only reason why we use it?
well, and it's clear as to which variable is the independent and dependent without having to state it expressly. So just like it's a little bit more specific.
Right. Yeah.
But there's not really much difference other than that. That's section 1. So just talking about what are some functions and representations for functions. In section 2, we're going to talk about domains and ranges. So if you remember from our definition of a function, a domain and a range is a set. One way that you can represent some sets is using interval notation. So if your set has any part of it that's continuous, interval notation is a convenient way to describe that part. When I say continuous, I mean like you're including all the values from like 3 to 4. So not just the numbers 3 and 4, but like 3.1 and 3.01 and 3.001 and everything in between. Everybody's okay? So the format for interval notation is you have lower bound, comma, upper bound. So a lower bound is a value that's smaller than everything, or I should say smaller or equal to everything in the set. And the upper bound is something that's bigger than or equal to everything in the set. And then at the end, you'll either have a bracket or a parenthesis. So you have a parenthesis if that lower bound value is not included. So for example, if you had a situation that was a strict inequality, like a less than or greater than. And we use the bracket if that value is included. So if you have like a less than or equal to or a greater than or equal to situation. And the same thing goes at the upper bound end, right? The same rule for bracket or parentheses. So I'm not going to write that part again. So let's just take some sets of numbers that I'm going to describe with inequalities and translate those inequalities into, or those sets into interval notations. Okay? And this is, again, something that we did in our Algebra 2 class. I think primarily we asked you to write your domains and ranges using interval notations last year. So this should also come as, something that feels familiar. So let's say we have x is less than or equal to 2. So if I was to describe that set, you have things like 2, -1, -0.075326, -27,419, on down, right? Everybody feels okay? So what would the lower bound for this set be? Paul?
Would it be negative infinity?
Yeah, negative infinity. So since it's a less than 2, you can always find another number less than something. So if we keep going all the way down in that direction, you land at negative infinity. The upper bound for this would be 2. Now the infinities always get a parenthesis, so we don't have to think too hard about that. And then the 2 should get a bracket because 2 is less than or equal to 2. It's a member of that set, so it should be included. And we'll be a little bit more specific with our notation than we probably were in our Algebra 2 class, where we were a little bit lax. So here, our set is x's. So we would say x is a member of that set. So that symbol there is like an E, but instead of having corners, it's just rounded. It just means that it's a member of that set, because again, an interval is describing a set of numbers.
So that just means member of?
Yeah. Yep. Yep. Or you could say element of. Some people say sets contain elements. You know, I like to use members because a lot of time, I like that word a little bit better because a lot of us have chemistry class at the same time, and we hear element and we think of something very different than just like a member, which is all we're really talking about. These are things that you learn after doing this job for whatever, 10 plus years. Let's do another one. So this is a compound inequality, right? Where we have negative 5 is less than y and is less than or equal to 10. So this set contains things like negative 4.99, negative 3, 0, 1.65, all the way up to 10, right? Everybody agree with that? So what would my lower bound to be for this set? Oh?
Parentheses negative 5, and the upper bound would be parentheses y. So
not y for the upper bound. Again, y is representing the members of the set. Well, since with the way that this one is written, we can just do 1, and that would be simpler there. Yeah, Grace? 10, yeah, perfect. Yep.
Split it up.
You'd have to be very careful about how you did it.
So if you're splitting it up, it would be y.
No.
No, why not?
You can't have a variable in an interval. An interval is like from this number to this number.
Okay.
Like what is y?
Okay.
You know what I mean? If you say negative 5 to y, what if y is negative 10? Then that makes no sense, right? You know what I mean?
Yeah.
If you did like negative 5 to 0 and then 0 to 10, like that would be potentially okay, but you'd have to be careful about like whether you're using a bracket or parenthesis on the tens and then the symbol that you're using in between them or whatever. But this is much simpler to just do 1. Okay. Negative 5, bracket or parenthesis? Parenthesis. Everybody good with that? 10, bracket or parenthesis? Bracket. Feel good there? So that's like an and inequality, right? Y is greater than negative 5 and less than or equal to 10. So both of those need to be satisfied. Let's look at another kind of compound inequality. This one is an or inequality. So this says it's either less than negative 2 or greater than positive 5. So things like 6, 7, 8 are good. And so are things like negative 3, negative 2, negative 4, negative 5. So this is an or inequality we're going to represent with 2 intervals here, since you have a gap in between in between the two parts, right? So we'll just write we'll use one interval for each inequality, and then we'll connect them with a symbol in the middle. So for a is less than -2, the lower bound there would be -infinity, and the upper bound would be, and then the -infinity always gets a parenthesis, and then the -2 also gets a parenthesis. Now, the symbol that we're going to use to connect these is like a U with no tail on it. That's the union symbol. It basically just means or in the language of sets. And then we'll just write our other interval. So a is greater than or equal to 5. The lower bound there is 5. And the upper bound is, okay, infinity. I write mine as positive infinities. It's not wrong if you just write infinity, though. It would be wrong if you leave the negative off of a negative infinity, but you don't need the positive there. I like to write it just for clarity's sake. And a bracket on the 5. Cool. Oops. We forgot 2 things on these. I forgot y is a member of, and here a is a member of. Again, just being a little bit more specific as we step up in our math classes with our notations, right? It's an awful lot to throw all the notation at you all at once the first time you're seeing it, but now that we're seeing it for a second or maybe a third time, add a little bit more notation, a little bit more requirements on the notation, so we're being just a little bit more specific about things. Common practice in mathematics, right? What we're going to do now is talk about a concept that we did not talk about directly in our Algebra 2 class. And then that topic is the difference between what we call an implied domain versus a relevant domain. So this is kind of new. We've maybe addressed this a little bit indirectly in our Algebra 2 class, but we'll be real specific here and talk about what it is. So in our Algebra 2 class, almost always when we're talking about, hey, find the domain for whatever, we were talking about a relevant domain. Like here's a simple rational function, write the domain and range for this thing. We're talking about relevant domains. Implied domain is something that you're going to get from the context of the situation. So like in that Algebra 2 context of like, hey, find the domain for this simple rational function, all you have is just like the equation written down. You just, the implied domain there is all real numbers. That you're in an Algebra 2 class, these are the numbers field that you'd be working with, and then you'd narrow down that implied domain to the relevant domain, looking at the specific operations going on in your function. So the relevant domain will always be a subset or equal to the implied domain. It would never be bigger. Okay? The place where we have to be careful with an implied domain is in a problem where there is context. So if we say the function f of x equals x represents the number of people needed to screw in a light bulb, there the domain has a different implication, right? We wouldn't be talking about real numbers, because if x is representing people, you can't have a negative person, right? You can't have 7/8 of a person. You're really talking about a situation where you have your domain would be the natural numbers, like 0, 1, 2, 3, 4, 5. Whole numbers only, no negatives. Does that make sense? Okay, we'll do some examples here just to kind of clarify these 2 concepts. So we're just going to be looking to write the domains in interval notation. I'm just going to write down some stuff here. Okay. So our first one we have f of x equals 2 times the square root of x minus 4. Here, there's no context given to this problem, so the implied domain would just be, well, be specific here. All real numbers, right? You're just looking at a function. You're in algebra trig. You're in a high school math class. There's no reason to believe that the context is anything different. Now, from that, we'll look at the relevant domain, right? So to figure that out, what I'm going to do is I'm going to look at what operations are involved in my function. So I see 3 operations going on. I see multiplication, I see subtraction, and I see a square root. Everybody see those 3? Okay. I'm going to think to myself, okay, if I multiply 2 real numbers together, is there a situation where I can get an undefined result, where I don't get another real number back? No, right? If I multiply 2 real numbers together, I'm always going to get a real number. What if I subtract 2 real numbers? 0 is a real number, though. That's fine. So no problems there either, right? What about square roots? If I square root a real number, will I always get another real number back, or could I get something undefined? You could get something undefined. What kind of numbers give us a problem when we square root? Well, what kinds of numbers give us a problem when we take their square root? Negative numbers. Very good. So what I'm going to do to determine my domain then is I'm going to take the part that's underneath the radical, and I know that that part has to be non-negative. So it could be 0 or it could be positive, but I can't have any negatives under there, because if I take the square root of a negative number, I get an imaginary result, right? You guys remember that from last year? Okay, so I can go ahead and solve this inequality by adding 4 to both sides. And now I'm just going to take this inequality and translate it into an interval. So here the lower bound is 4, and the upper bound is positive infinity. Since 4 is greater than or equal to 4, I know that the 4 gets a bracket. And the infinities always get a parenthesis. And then I'll just write x is a member of. And that's my relevant domain. Paul?
Over like
So this problem has no context to it. So we just assume that we're working from the real numbers, because that's what we, if you're going to do anything with a function in math class and you're not given any context to it, you always can assume that, like, okay, I'm just going to be plugging in like anything I want. You know what I mean? Like there's no, and we'll do an example here coming up where it does have some context. Yeah, so we can see the difference there. Yeah, no problem. So again, g of x equals 3x over x plus 2. No context to this problem is given. You're just given the function. So your implied domain, again, would just be all real numbers. To figure out the relevant domain now, I'm going to look at the operations involved in the function. What operations do you see? I see 3. What 3? Division, multiplication, and addition. Now, multiplication we've already established. There's no problems there. How about addition? No problem. What about division? Can I divide any 2 numbers? No. What could give me a problem? Mia? Yeah, if I divide by 0, that's a problem, right? You get an undefined result if we divide by 0. So what I'm going to do is I'm going to take the denominator of my fraction, which is the same thing as the divisor in my division problem, and say that that cannot be 0. Everybody okay with that idea? I'll solve this by subtracting 2 from both sides. And now I would like to write an interval for this, but the problem is that this isn't written as an inequality, right? Well, I'll just write this now as an inequality then, and so it'll be easy to write the interval for it. So if I think about x cannot equal to -2, that's everything less than -2 is okay, and everything greater than -2 is okay. So I'm just going to break this up into an or inequality, where x is less than -2, or x is greater than -2. Everybody agree that that's the same thing as x is not equal to -2? And we just showed you guys how to do this, so I'll have negative infinity as the lower bound to -2. Both of those are parentheses. Then I'll have my union symbol, and then my lower bound is -2. My upper bound is positive infinity. Both of those are parentheses. And I'll write x is a member of. Questions so far on anything we've done? We doing okay? Again, if there's something that you can't read penmanship-wise, or you don't understand, or you want to follow up about, or whatever, just shout it out. No reason to be shy. If you don't understand or you can't read it, I'm sure somebody else is in the same boat. Somebody's got to ask the question. All right. My last example of this is the function v of s is equal to s cubed, where v of s is the volume of a cube with side length, edge length s. Here we're given some context about the independent variable, right? So immediately we see that there's some extra information here. This extra information is going to be used to determine its implied domain. So again, the independent variable is s. In my description here, I'm told s represents the edge length of a cube. So what kind of numbers can s have? Or what kind of numbers can s be? Oh, positive, right? I would also include 0. I'm not sure how we defined a cube in this instance, if something with 0 edge length and 0 volume would represent a cube or not. But I'm going to include it for this example. Whether I wouldn't mark it wrong one way or the other if you included or didn't include 0 in that context, because we haven't clearly defined in this situation what we're counting as a cube. But yeah, so we'd have our interval would be then 0 to positive infinity. And whether you want to use a bracket or parenthesis at 0 would be, in this case, I think either is fine, because we weren't super duper clear. Paul?
It's 0 because it's a volume, so you can't have negative volume.
Well, s is an edge length, and you can't have negative length.
Negative length.
Right. Perfect. Yes. Exactly right. Everybody's good with that? So again, like, there's no mathematics we did there. We just used a little bit of common sense about the context of the problem, right? Like, what is actually physically possible if I'm going to measure an edge length? Well, can't have negatives. Now, if I look at the relevant domain here, I'm going to go ahead and look at the function. I see only one operation going on there, cubing, right? Which is really just repeated multiplication. Everybody agree with that? S cubed is the same thing as s times s times s. And we already established that multiplication doesn't pose a problem. So the relevant domain in this case is going to be the same as the implied domain, because the only operation going on was really multiplications, and we already established that multiplications of real numbers just gives us another real number. It's going to be fine. Is that okay? So there's not much to do with that one. It actually turned out to be, like, in a way, the easiest one, even though it, was a little bit, we had to think about it a little bit, but there was no computation to do. Oops. Yeah, that's good. Everybody feel okay? Now let's go back and do the ranges for these. So the ranges are always, well, I shouldn't say always. The ranges are typically going to be a little bit trickier to find than the domains. And when I'm looking at trying to find ranges, what I like to do is try to determine where my function is increasing and decreasing. So just as a review, let's say this. Let's call this guy f of x. So this function here, f of x, is increasing because as you move from left to right across the graph, it's going up. Everybody's okay with that? Just like it's uphill. And let's say that, oops. Call that guy g of x. G of x would be decreasing. Again, because as you walk from left to right across the function, it's going down. Everybody's okay with that? So the domain for our f of x in this example is like, let's be specific, is a to b. And the domain for our g of x in this example is c to d. Everybody's okay with that?
Why is it x?
Well, the x is the independent variable in both cases, right? Okay. Now, if I want the yes, Evan. Of course, yeah. Now, if I'm talking about the range for my f of x, the smallest y-coordinate is going to occur when the x is equal to a, right? And the biggest y-coordinate is going to occur when f is equal to b. Does that feel okay there? F of x is a member of, that's just that member symbol. And then I have the parenthesis f of a, comma, f of b with the bracket. So notice the bracket and the parenthesis stayed with the a and the b from the domain. But let's look at what happens with the decreasing function here. So we have g of x now, or if you wrote y, that would be okay still too. I'm going to write g of x and f of x though, just to be specific so that you know which one we're talking about. So the shortest or the smallest y-coordinate happens when x is equal to d, right? So I'm going to have, g of d, and I have the bracket there because the bracket is going to come with the d from the domain. And the highest part of that graph happens when x is equal to c. So my upper bound is going to be g of c. And then the parenthesis from the domain is going to go with that one. Mackenzie. Yeah, so the open circle implies that it's not included. So that's why I put parentheses there. And the filled in circle tells me it is included. So that's why I have the bracket there. Yep. So it's the same idea as you remember back in like your algebra or pre-algebra class when you had like x is greater than 5. You had like 5. You drew the open circle with the arrow. And then if you had like x is less than or equal to 7, you had like the filled in circle with the arrow. It's the same idea with the filled in endpoints on our graph. We're just borrowing that same kind of notation. Does that ring a bell?
I just couldn't see the.
Oh, totally fine. Totally fine. Paul?
So why don't you write it x is c comma d, and then go g of d comma
Because d is where we have the smallest point. It's the smallest y-coordinate, right? So that's the lower bound. So the lower bound there is g of d.
Okay.
We'll do a numeric example here in a second that'll be easier to kind of see what's going on.
Well, wouldn't you want to do the same thing for x?
Well, if I look here, the shortest or the smallest y-coordinate is at A.
No, when you wrote it like c comma d.
Well, C is the furthest left point.
Oh, that's what.
Right? Domains are x's.
That's
So
okay.
the domain is left and right, and the range is up and down.
Yeah, that was my bad thing.
No problem. Again, it's important that we understand what we're seeing. The takeaway here, though, is if I have an increasing function, I can find the range by just looking at the endpoints of the domain in the same order that they occur. And if I have a decreasing function, I again can find the range by looking at the endpoints of the domain, but I have to flip the order. That's the big takeaway. So very important that we're able to determine whether our function is increasing or decreasing, because that allows us to determine how we would find that range. So I'm going to use the same functions that we looked at for the domains because, well, we already found the domains, right? So it just saves us a step because you can't really find the ranges until you find the domains. You know what I mean? Okay. All right. So what I need to do here is take a look at my square root function here that I'm given, my f of x, and try to determine whether this is increasing or decreasing. Now, if you remember what we did last year in Algebra 2 class, and you remember what the graph of this looks like, that could be quite helpful for us. So if you remember back to our Algebra 2 class, a square root function is just like one of these, right? And it's either going to go, that way or it's going to go that way. You know what I mean? You guys kind of remember the shape? Okay. Do you remember which way or what the conditions are that we get something that's shaped like the red one versus the blue one? The leading coefficient. Very good. So if the leading coefficient is positive, we get the increasing version, and the leading coefficient is negative, we get the decreasing version. So this tells me that we have the increasing situation. Everybody still on board? Okay. So the lower bound for my range is just going to be found by looking at f of the lower bound for my domain. And the upper bound for my range is going to be just using f of the upper bound from my range. So the lower bound for the range is 0. Everybody good there? I skipped doing some arithmetic, but I think in this class that's probably fair. What's weird though now is I have f of positive infinity. Well, we're just going to use a little bit of common sense to evaluate that. So I have 2 times the square root of positive infinity minus 4. What's infinity minus 4 going to give us? Still infinity, right? You have infinitely many things and you take 4 away, well, that's still infinite. The square root of infinity. Still infinity, right? Like the square root makes the number get a little bit smaller, but it's infinitely big anyways. So then you have 2 times infinity, still infinity. And since we're dealing with an upper bound, I know that infinity must be positive. If you're dealing with a lower bound, the infinity must be negative. Everybody's okay with that idea? Why is that the case? What would it be saying if my upper bound was negative infinity? Your interval would have to be empty, right? If the biggest number in it is negative infinity, then there's no numbers that can be in your interval. And like, what are we doing here, people? Then, yeah, there's nothing there. So like, if you have a domain, you can't have an empty range. You know what I mean? It has to have something in it. So what I can say then is just f of x is a member of 0 to positive infinity. And again, I'm using the bracket on the 0 because the bracket on the 4, which is where the 0 comes from, right? Likewise, the parenthesis on the positive infinity, because we got the positive infinity from plugging in the positive infinity to have the parenthesis.
So why did we decide to put in 4 for the lower bound?
That's what we found up here, is that to find the endpoints of the range, I'm just going to use the endpoints from the domain. Since the function was all increasing or all decreasing. If it was, well, we figured it out by remembering what we knew about the shape of the graph. Okay. If that was not the case, it would be a little bit more difficult, because then you'd have to split the domain into like a part that's increasing and a part that's decreasing. But you could still do it that way.
So, why 4?
So you're good with YA here and f of A, right?
Yeah.
Here's A, here's f of A.
Oh, okay.
That's all we're saying.
Oh, I see.
Okay.
Just kind of borrow.
I'm doing the same thing as that we established earlier.
I got you. That makes sense.
Yep. We're just using specific numbers now. Okay. Next one we had here. And what was our domain? That was negative infinity to negative 2 union negative 2 to positive infinity. All right. So again, what I want to do is determine where or when is this function increasing or decreasing. If I remember back to my Algebra 2 class, this is in the form of a simple rational function. Because you have degree 1 polynomial over degree 1 polynomial. All simple rational functions have a vertical asymptote and a horizontal asymptote. So, you know, something like that, right? And then you're either going to have hyperbolas that are kitty corner from each other, either like this, or they might look like this. The takeaway is that this one, the blue, is if the leading coefficient over the leading coefficient is negative, and the green is going to be leading coefficient over leading coefficient is positive. Again, I didn't really care where the asymptotes were. I just wanted to remember kind of what the graph was going to look like. We'll review in second semester how to deal with these rational functions and graph them again. But right now, I'm just trying to keep it a little bit vague because I don't need a lot more information than that. So if I look at this particular problem, my g of x, the leading coefficient in the numerator is 3, and the leading coefficient in the denominator is 1, which is 3 over 1 is positive. So we're going to be dealing with the green arrows, or the green graph. Everybody okay with that? If I look at those green graphs, if either piece, as I move from left to right, are heading down, everybody agree? So they're both decreasing. So it's decreasing the whole way through. So for my range, my lower bound for the first part is going to come from the upper bound of the first part. And the upper bound for the first part of my range is going to come from the lower bound of the first part. Everybody's okay? Because it's decreasing is why I switched the order of the inputs. Again, we established that earlier. Okay, so if I do g of negative 2, and just plug in negative 2, that's negative 6 over 0. Uh-oh, is that a problem? Not really. So if I have something, if I take 6 things, I'm going to just remove the negative for the analogy here, and I want to divide it up into 0 parts, you're basically like chopping it infinitely small, right? Does that kind of make sense? If you take 6 and divide it into 2 parts, you're going to have 3 and 3, right? If you take 6 and you want to divide it into 0 parts, you're just going to have to chop it like infinitely tiny and infinitely small. So this is essentially going to be an infinity. The question becomes, should it be positive infinity or negative infinity? Well, because we're talking about a lower bound, the sign on that infinity must be negative. So if you have something divided by 0, it's going to tell you that that's infinite. It's infinite. Your question becomes, is it positive infinity or negative infinity? And you can tell by what bound it is. So lower bounds are always negative infinities, and positive bounds are always, or upper bounds are always positive infinities. Does that feel okay? Do the same thing now for the g of negative infinity. So if I think about this, negative infinity plus 2, well, that's still negative infinity. And then 3 times negative infinity divided by negative infinity, well, it's just 3. So if I do the next one, the lower bound for 2 is going to be positive infinity, and the upper bound for the second interval is going to be g of negative 2. But we've done these both already, right? So I'm just going to skip the arithmetic there, right? We did g of negative infinity. G of positive infinity is going to give me the same thing. Should be easy to see that why. And g of negative 2 we already did. I'm getting a positive infinity this time, though, because it's an upper bound rather than a lower bound. So when I put this all together, I have that. So we need to scroll up. If you can't see, holler at me and ask me to scroll up. I'd be happy to do that kind of stuff. I know sometimes when you're in the back or whatever, you're playing dodge ahead or whatever to see the bottom of the screen sometimes. So if you're having trouble, holler at me and I'd be happy to accommodate. Our last example was this v of s, and I'm gonna not write the extra condition on that, if that's okay with you guys. So again, first thing I want to do is think about what the graph of v of s is going to look like, or v of s is going to look like, so I can determine whether it's increasing or decreasing. This one should be fairly easy because it's just a degree 3 polynomial. If you guys remember, like x cubed, or y equals x cubed, kind of looks like this, right? Now this is a little bit simpler because really we only have this part of it, but pretty easy to see that that's increasing, right? Just as a aside, on any of these where I've been looking at the graph to try to tell what's going on, you could certainly graph them on your calculator if you didn't remember exactly what these things were going to look like. That's a big ask from a year ago, to remember specifically what these graphs would look like. I choose to do it by my head because I like to try to refer back to the things that we've already learned, because I think that building those connections out, I think, is helpful for you guys to review it again. But like from a pragmatic standpoint, like there's nothing wrong with being like, I think it looks like this. Oh, let me check on my calculator, you know. So this should be fairly easy. I just need to do v of 0 and v of infinity to get my lower bound and my upper bound. Well, 0 cubed is just 0. Infinity cubed is just infinity. So my range is the same as my domain was. Not shocking, considering it was an odd polynomial. Or if you're just thinking about volumes of a cube, right? Can't get negative, just like the side length couldn't be. And as the side length gets bigger, the volume's going to get bigger, and you can get the set edge length as big as you want, so the volume can get as big as you want. So like not shocking, it's the same there, right? Okay. Section 3. This will be the last section we do today. This is on the idea of continuity. So we say that a function is continuous if you can draw it without having to pick up your pencil. So there's 3 different situations that might cause you to have to pick up your pencil when drawing a function. We call those situations discontinuities. Two of which you've seen last year. So the first kind is a removable discontinuity. We saw this when we graphed general rational functions. So imagine like a removable discontinuity. You have your graph, but there's like a break in it. There's a point missing. So that missing point I'm representing with the open circle there, just like we did in my increasing and decreasing example from a moment ago. Or sometimes this wouldn't have been a situation that we saw last year, but your graph could have that break in it, but the point is still there, it's just in the wrong spot. Keep in mind here that these guys have to be on the same vertical line. Why is that? If they weren't, it would fail a vertical line test, right? Joe? Of course. Okay. The next kind is a jump discontinuity. Discontinuity. So what this looks like is, that's right, have some function, and instead of just missing one point, you're missing like a section of the graph. Worth pointing out here, these endpoints here could both be open. One could be open and one can be closed, but both cannot be closed because you'd fail a vertical line test again. Assuming that they're stacked right on top of each other like that. If they weren't stacked on top of each other, I guess they could both be open. Or both closed, excuse me, and still be okay. You guys get what I'm saying? So if you have like this, and like, you know, there's some gap there horizontally, that would be okay for both of them to be closed then. The last one is called an infinite discontinuity. And basically what we're talking about here is like a vertical asymptote. And I want to be clear when I say this that not all vertical asymptotes are discontinuity or infinite discontinuities, but all infinite discontinuities are vertical asymptotes. Come on. Come on. There you go. Can you guys think of a situation where you have a vertical asymptote that's not a discontinuity? You saw this last year in your Algebra 2 class. That's probably the topic you felt the least familiar, or you have like the least remaining familiarity with. Typically, that's my experience. Logarithm. If you look at the graph of a logarithm, there's a vertical asymptote, but the whole graph is on just one side of the vertical asymptote, so it can still be drawn without having to pick up your pencil. So there's just to illustrate that vertical asymptote doesn't mean infinite discontinuity, but the infinite discontinuity does mean vertical asymptote, right? One set is bigger than the other, although it does contain the other one. So example, like what this function might be. So again, like any simple rational function has an infinite discontinuity. You know, something that kind of matches the graph that I drew. Jump discontinuities you had not seen. And the reason you had not seen is because to make a jump discontinuity, really the easiest way is to use what's called a piecewise function. So for a piecewise function, you describe a function in two ways. You know, like, let's say square root of x minus 3 plus 2 is about what that looks like for x greater than 3. Or you could have negative 3 minus x minus 2 is probably what that looks like to me for x less than 3. So basically what you're saying is for this part of the domain we do one thing, and that part of the domain we do something different. Not super duper important that you're able to deal with any of that right now. I'm just kind of talking. And then the removable discontinuity, we saw that when you had something like, again, let's try to come up with something that looks ish like this. Was something like this, right? Where you could reduce out some factor completely. So if you look at what's left after that reducing, it's that parabola, x squared minus 4, but there's a hole at negative 3 when x equals negative 3, which is about-ish what we drew there. We're going to stop here. So for the first assignment, as part of your Sunday homework check, is just going to be 1 through 12 from the problem set. That's already up on My Notre Dame. And now all of a sudden OneNote is like decided to not recognize my stylus. And again, to find that homework assignment, if you look in the content library, the homework problems are in there. Again, you can move this into your homework tab and do your homework in OneNote, totally fine. If you choose to do that, please, 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 please write your answers like in a separate column with some work associated with them. Don't just like try to scribble some stuff in right next to the problem, so I can't really make any heads or tails of what it is that this is there. Paul?
Could I just Is it okay to take a picture for that one?
Yes, the other option, if you don't want to work in OneNote, is you can certainly do it by hand, take a picture, and then drop it into your homework folder. Also, totally fine to do things that way. I have no preference one way or the other. Both are fine. The due date on the homework is Sunday, midnight. And make sure that you remember to sync your notebook after you finish your homework assignment, and wait for the OneNote to clear its sync before you jump on out of there. Thank you guys for today. You did a nice job. I like the participation, everything else.